Gauss's law, suppose I have a point right here with some charge q. And I am looking at if I have some sort of locus of points, all equidistant from this, in other words, a sphere, so some distance r. What I wanted to figure out is what is the electric field at this point. Well, it's simple enough. I have a charge here. I'm the same distance away. The electric field would be pointing away from it. And so my electric field is k q over r squared in the r hat direction. So if I wanted to figure out what is the electric flux through this surface right here, I know that the electric flux is equal to the integral of E dot dA. Now, at any particular point, dA, if I think about dA is a differential of the area at where the electric field is acting, and for a closed surface, it is outwards. Or if I'm over here, my electric field is pointing in this direction, but my area vector is also perpendicular to the surface and pointing outwards. So in other words, wherever I am on here, my electric field at that point and the differential for the area are in the same direction. So this just becomes the integral of E dA. Well, my electric field, since that's the magnitude here, is the same if I'm equidistant from the point. So this just becomes E dA. And so I'm integrating over for the area, which goes from 0 to the total surface area. So this just becomes E times the surface area, which is 4 pi r squared, which is equal to, that's the magnitude of my electric field. So this is k q over r squared times 4 pi r squared. The r squareds cancel out. And so I'm left with 4 pi k q. Don't forget, this electrostatic constant can be written a different way. So I have my electrostatic constant is also equal to 1 over 4 pi epsilon sub naught. In other words, 4 pi times my electrostatic constant here is equal to 1 over epsilon sub naught. Hey, I just happen to have that right here. So this becomes q over epsilon sub naught. Now, this is not the formal derivation of Gauss's law of electricity, but it does show, at least in this case, that my electric flux through a closed surface, this is a complete sphere here, so the electric flux through a closed surface is equal to the charge that's enclosed divided by epsilon sub naught. And that is Gauss's law. So the electric field through a closed surface is equal to Q enclosed over epsilon sub naught. One other notational thing, I could have symbolized the fact that it was a closed surface other than doing it by writing CS for closed surface. So I could also have written a circle here, and this indicates this is a closed surface. So that would show up there and there. And even though this is derived for a specific case, this is actually a true statement. This is one form of it, or you could also write it as the integral E dot dA is equal to the enclosed charge over epsilon sub naught. That's a slightly more formal way of writing Gauss's law of electricity. And let's just write that up because it is important enough. Gauss's law of electricity. There's a reference in the reverse roadmap that you watched early on, which talked about Maxwell's equations. Well, this is the first of Maxwell's equations that we will derive in class, and the others will derive, that we pseudo-derive in class. And we will hand wave through a couple others, do some pseudo-derivations for that as well, but this is the first of them.